Good afternoon, everyone. And yeah, thank you to the organisers very much for the invitation. It's been a wonderful workshop so far. So I'm going to be talking about the evaporation of arrays of non-circular droplets. So this is work that I've been doing over the last few years with several of my collaborators. So Madeline Moore, who we've already heard from Loughborough University, but also Stephen Wilson and Brian Duffy from the University of Strathclyde. So let me just start with a brief question to sort of try and emphasize why we wanted to look at this, which is sort of what the following problems have in common, which is, so if you look at, say, a cylindrical punch indenting on elastic half space, if you look at electrical contact resistance, if you look at the thermal flux around a plate at constant temperature, or the potential around sort of a plate at constant potential, constant voltage, if you look at the dissolution of microbubbles, or if you look at the electrical polarizability of apertures, you find that it turns out they actually satisfy exactly the same governing equation and same boundary conditions, which is sort of what we're going to be looking at today, but in the context of evaporating droplets. So there's an interesting sort of multiphysics connotation of what I'm going to be talking about today. So as I say, today I'm going to be talking about droplets. They're ubiquitous in industry, usual slide, insert usual stuff here, but they're sort of hopefully very interesting. From a theoretical background, we sort of know roughly how a droplet evaporates. So we know that even if you have so this is the classic coffee stain effect that we've heard about several times already. So if you have a puddle of coffee, if you have a droplet of coffee, and you let it evaporate, even though the particles are initially uniformly dispersed, probably through the liquid, as the thing finishes evaporating, you find this very heterogeneous distribution with a preferential concentration close to the contact line. And this was sort of explained, originally by Deegan in '97, and there are basically three key steps and three, different parts of the physics to understand in order to sort of, understand how this works. So the first thing is you need to calculate the evaporative flux. Once you've determined that, you find that the shape of the droplet is set by surface tension, and so you can determine the liquid flow within the droplet. And then, you can just calculate an advection diffusion equation for the particles inside the droplet to determine how they move. And you find that, because of the preferential evaporation at the contact line, the flow towards the contact line, and the particles are convected there. Terrific. And so, as of 2018, we felt pretty pleased with ourselves. We felt like we had a good understanding of how these systems worked. And then Merck approached us and said, can you do the same thing for AMOLED screens? So it turns out that some of these AMOLED screens are manufactured by printing the pixels as liquids and then letting them evaporate. And so you have these enormously large arrays of non-circular droplets. And we sort of said, because unfortunately this wasn't something that we had the technology to understand. In particular, there are several major outstanding problems in understanding this. So for example, there's the evaporative problem. We didn't know how to deal with multiple droplets or non-circular droplets. In the fluid problem, Deegan's sort of formulation for the flow didn't allow for axisymmetric flow, didn't allow for asymmetric droplet shapes. And the particle problem, the particle transport problem, as we've heard discussed, we had issues with understanding diffusion, deposition, and jamming, which, again, Madeline's talked to us about already. So I'm going to focus on the problems of the multiple droplets and non-circular droplets and maybe touch a little on the flow problem. So first, in order to understand what problem we're actually solving, we need to know the evaporative model. So this is what we're going to look at what we call slow evaporation. So Luca's already given us a nice talk about the difference between diffusion limited and transport limited evaporation. We're definitely looking in the diffusion limited regime. So this is sort of, as we say, inverted commas, slow evaporation. This is sort of what you think of when you just have sort of droplet evaporating into ambient atmosphere. And so it turns out that the evaporation is basically Fickian. So there's a flow of liquid from the surface of the droplet down the concentration gradient at the surface. So C is the concentration of the vapor in the gas phase, and it satisfies Laplace's equation subject to, after some sort of non-dimensionalization, some sort of saturation condition at the interface, a no flux condition on the substrate, and then some decay condition at infinity. And as I say, in general, this is a saturation concentration, but we generally just use a non-dimensionalization where it's unity. So this is great. In principle, if you can determine the concentration in the atmosphere, you're in good shape to be able to determine the gradient of the interface, which gives you the evaporation rate. And in principle, this seems reasonable, right? Laplace's equation is not too bad. We don't have to solve Laplace's equation, separate variables, everything's fine, except that this sort of mixed boundary condition on the substrate makes life very difficult. Now, everything I'm going to talk about here today is going to be for relatively thin droplets. I can talk about the thick droplets if you want. So what existing solutions were there? So in 1873, Weber solved this for what was effectively a flat droplet. And this, you really can do whatever you want, Green's functions, dual integral equations, any method you use will get you a solution. And you can extend this to flat elliptical droplets. And then there's this solution by Popov from 2005 for a spherical cap. So if you take a sphere and cut it off, that's roughly the shape you'd get of a droplet that was dominated by surface tension. But even then, the solution is actually only a numerical quadrature in terms of sort of these conical functions, which are actually remarkably hard to calculate. And as far as we know, that was sort of about it as of, 2020, something like this. So if we wanted to set about trying to generate some new solutions, how would we do it? So as I say, we're going to look at droplets that are sufficiently thin that we can assume that to leading order they're flat. And the idea is actually not really to solve for the concentration in the atmosphere, but just solve directly for the flux. And so we do this by posing the whole thing as a Green's function formulation. So if you've got multiple droplets, say A1 and A2, then the concentration anywhere in space can be determined for an appropriate Green's function formulation. So integrate, pick a symmetric Green's function so that Neumann is satisfied automatically everywhere on the substrate. And then when you do your sort of Green's theorem, you get that the concentration anywhere in space can be written as the integral of the Green's function times by dc dz on the surface of the droplets. And if you remember, dc dz so this is the gradient of the concentration at the surface. This is actually, as it turns out, the negative of the flux that we want. And so what this means is that this thing, this dc by dz, this is the negative of the flux, this is the quantity that we want. But this concentration, if you evaluate it on the droplet surfaces, we know that that's just the saturation concentration. That's generally unity in our non-dimensionalization. And so this is effectively an integral equation for the evaporative flux. It's not a particularly nice thing to try and solve. This is a fiddly kernel. But it turns out there's a decomposition due to Copson, which lets you write your Green's function, your basically 1 over distance, in terms of this integral. So very helpfully, we've turned a double integral equation to a triple integral equation, just what you want to do to start off with. There's this funny thing, the L function. What this does is effectively insert a term of the form x squared on rho prime in front of the nth Fourier mode. It doesn't really matter, but that is what it turns out to be. But so now the key thing is, can we solve this integral equation? So let's look at a slightly simplified case. Let's just look at a single droplet, circular footprint. And then in that case, it simplifies to look something like this. And the key thing is here, and the reason this decomposition is quite nice, is because these two 1 on square root things are now Abel type transforms, if you're familiar with those. This is an L-type problem. And so both of these have standard inversion formulae. And so this is now something that you can invert explicitly. And so if you do, it's just this. And it simplifies down, as I say, for the single circular droplet, you get something that looks like roughly some constant on root 1 minus r squared. And this is a classical result. This is exactly what Weber predicted. And so it says that the evaporation is minimal at the center of the drop and then square root singular at the edges. Terrific. So what can we do if we want to do sort of a more sophisticated case? So let's have a look at the multiple droplet solution. So how do we do multiple droplets? Well, we basically take the same approach. So from a physical perspective, why should multiple droplets interact at all if you just have two droplets sitting next to one another? And the answer is that, of course, everything's happening here in the vapor phase. So if you have a single droplet, it just sort of has, if you imagine the contours of equal concentration around it, when you have two droplets sitting next to one another, those fields are going to interfere with one another. It's an effect that we call shielding. So the effect of the concentration due to this droplet is going to sort of impede the negative gradient here. It's going to impede the evaporation of the other droplet. And so so I say we call this effect shielding. So how do we solve this? Well, we basically take the same approach. So we use the Green's function formulation that I just talked about, and you start trying to invert. And if you work hard enough, you can get it down to this Fredholm integral equation. Unfortunately, this you can't solve, so you do have to make some sort of approximation. And so what we do is we assume the droplets are relatively well separated. If you do that, you can either take the integral again over the whole thing twice to get a relationship between, so F is the total flux from each droplet, or if you don't, you can get the local flux from each droplet. So how do these perform? So actually pretty well. So here we've got a comparison of the total. So we've got two droplets. They're distant. They're radius 1, center separated by a distance b. And all I've done is plotted the flux as calculated by our asymptotics and the exact results of Kobayashi. And you'll actually see that although we assume that the droplets were nominally well separated, actually all the way down to b is 2, where the droplets are touching, the agreement is excellent. As I said, there are actually two lines here, although they're very difficult to see. And so we've just plotted the error. And the error is always less than about 0.4%, right down to the point of touching droplets. So this is good encouragement for using this method. A couple of little examples of how you can use this. You can use it to determine lifetimes. So as I think many of us know, if you want to determine the evolution, you have both the radius and the contact angle that can change in time. So you need some sort of closure for these simple models. So you can look at we look at 3 different cases. So a constant radius mode where the droplet evaporates while its radius changing, constant angle mode where, again, the angle is constant, or a stick-slip mode, which is actually probably the most physically realistic, where it evaporates in one and then transitions into the other. And that lets you calculate things like droplet lifetimes. So this, for example, is the lifetime of 2 droplets as a function of their separation distance. And so you can see that when the droplets are closest together, so when b is minimal, they experience the most shielding because they're closest together, which extends their lifetime the most. Or you can look at, say, more complicated systems like rows of droplets. Here with constant angle mode, and you notice that the outermost droplets evaporate first because they experience the least shielding. They're on average furthest away from the other droplets. Least shielding, fastest evaporation, shortest lifetimes. So we want to do some experimental validation. So we compared against missed the reference, by some calculations, some experiments by Dora Khalifi's group, where they looked at sort of this eye-shaped set of droplets. So this is a comparison between sort of their extracted numerical experimental data and our asymptotics. Again, pretty good, except just near the end. And this is a comparison of the droplet radii and contact angles. So again, pretty good agreement. This gives us good confidence everything's working as it should. However, more interesting than the integral flux, because that was all based on just the total evaporation rate, the more interesting thing is to look at the local evaporation rate, because this is really sort of the acid test. And so, again, similar thing, if you do some numerics and some asymptotics, you find that everything is sort of pretty much bang on. Nice to see. And the nice thing about having the local evaporation rate is you can start to do things like determine flow inside the droplet, determine coffee stain type problems, this kind of thing. So let's have a go. So you can start solving the problem asymptotically. It turns out that basically flow just travels down the pressure gradient as you'd expect, where the pressure gradient is effectively dictated by the evaporative flux. And while you can technically write down the flow velocities, it's in terms of quadratures of hypergeometric functions, so it's a little bit grim. The key thing is that because we're assuming that, so we're going to ignore diffusion inside the droplet, particles are just convected along streamlines. So what that means is, normally you'd have to solve some fairly nasty equations, try and determine exactly how the deposition behaves here. But for our problem, because streamlines are constant and particles are convected exactly along them, turns out the mass between, say, phi is 0 and some point on the contact line is just exactly the total mass in between those two streamlines. All that mass will get convected to the contact line somewhere in that region. So if you compute this mass as a function of phi and take the derivative, that effectively gets you a measure of the local residue. And so if you do this and calculate, it turns out that, for example, where the droplets are closest to one another, so this is theta is 0, where the droplets are nearest, you get most shielding, least evaporation, least flow, least particle transport, least deposition. So yeah, this is exactly the shielding effect causing least deposition where they're closest and most deposition where they're furthest away. So, okay, that seems plausible. Doesn't actually agree with experiment. We got a bit lucky. So there are lots of pictures like the upper picture here where people do sort of experiments and show sort of the deposition. But the problem is because there's basically total saturation on the contact line, we don't know how thick this is. So we don't really have a good measure for what the deposition rate, deposition is locally. But Pradhan and Panigrahi in 2015 had this other picture where actually there's non-zero transmittance everywhere throughout the domain. And so it turns out that using the Beer-Lambert law, you can back out the local concentration, local residue. So we take the 20% of each drop nearest to the contact line, calculate density, and compare it against our asymptotics, and it looks reasonable. If you average and symmetrize, you get something that's really pretty good. So again, where the droplets are closest, minimal evaporation, minimal residue. So this is a good indication things are working as they should. Okay, so the other component of this is how do we deal with non-circular droplets? And this is something that people have sort of wanted to look at for ages. You know, there was a picture of this back in Deegan's original 97 Nature paper. So we're going to take the same approach, essentially. So again, we're going to try and invert the Green's function formulation. The problem that you have now, although it might not be obvious, is that the upper limit that you have is no longer unity. You're normally integrating over the region of your droplet, and for a circular droplet, that's integrating from R is 0 up to R is 1. But now the shape of your contact line is a function of the azimuthal angle. And it turns out that completely breaks inverting the L operator, like pretty much irreparably. So what do? We assume that our droplets are nearly circular. Nice bit of asymptotics again. If they're nearly circular, then at leading order to leading order, they are circular. And so you find that at leading order, you exactly get just the constant square root behavior. And then what you can do is you can basically just pass the corrections higher up the orders. And if you go up to sort of second order, you can get sort of a suitable result. And so what happens? Well, here I've plotted, these are monochromatic footprints. So the red lines are the footprints of the droplets. And again, I've plotted sort of two sets of lines. So there are solid lines, which are FEM and consol, and dashed lines, which are asymptotics. And they pretty much overlay one another, so you can't really see that they're both. But again, the agreement's pretty good. When it's monochromatic, life is okay. These are the results. Everything sort of works okay. It's a little bit more fiddly for the polychromatic case. But if you, have a bit of self-loathing, you can get through it, and it does work. And so then you can't do sharp corners, but you can do things that are very weakly smoothed. And so, for example, here are comparisons of, and again, so these are contours of flux. So the flux is sort of square root singular, maximum at the contact line, minimum at the center, and we can determine this for squares. So for anything sort of square, pentagon above, the agreement's pretty much spot on. So what we've done is we've plotted some more difficult shapes to sort of show the limitations of the method. So for example, something that's highly non-convex like the star shape, or something with really quite a sharp corner over here, you do get some disagreement. But given that the asymptotics are explicit, you're instantaneous, and the consol is half an hour, I thought this was not bad. The other nice thing about the asymptotics is, of course, it lets you make analytical statements about how the system behaves, how the evaporation behaves. And so what you can actually quite readily show is that, for example, the contours close to the contact line actually are exact mirror images of the contact line. But at the center, they're obviously not. And so it begs the question, what shape are these contours close to the minimum point? Because we've got at least a circle here and something elliptical here. Could you get something else in principle? And it turns out the answer is no. The n is 2 mode is special. So you can either have sort of a circular contour close to the center, or you can have an ellipse close to the center if the footprint of your droplet has a non-zero n is 2 mode. But that's it. Anything else will get killed off. So for example, the n is 5 mode here does indeed get killed off close enough to the center. Last little bit of validation. Back in 2017, Pedro Sáenz did some nice computations where he looked at the deposition from non-circular droplets. And at the time, we sort of did some numerics, got some hand-wavy agreement. But with our new techniques, we can do a lot better. Out of interest, again, the same principle holds true. What's happening is, closest to the corners, there's the most space to evaporate into, maximum evaporation, and hence the maximum liquid flux towards that corner, and to the maximum deposition. Similar sort of qualitative phenomenon. But so the question is, as I say, this was sort of hand-wavy numerics that sort of used, The question was basically, could we do better? Could we get quantitative agreement? Because it's only really qualitative. And so it turns out that you can. I think Madeleine's actually already showed these pictures, but on the left is the experimental data extracted using Beer-Lambert, and on the right is the asymptotics. And if you overlay them over one another, again, the agreement's pretty good. And so, as expected, at the corners, at the apices, maximum deposition. The question is, can you couple both of these? Again, it's a little bit fiddly, but if you go back to the technique, you can. And you can start to do arrays of multiple polychromatic droplets. And so as you see here, the centers are now offset, the minima are offset from the center because of the shielding effect of the other droplets. And the agreement's pretty good, basically everywhere except the triangle. In the triangle, there is some imperfection, basically because sharp corners are eventually quite tough to deal with, because the decay of the Fourier modes is very slow here. But other than that, the agreement's pretty good. Okay, so just very briefly, I'm nearly done, but I just wanted to go back to the first problem, which was the one that Merck posed, of how can we analyze this problem? And the main problem here is actually not so much the shape of the droplets as the scale of the array, because for an 8K resolution screen, you actually end up with roughly 100 million droplets being deposited. And so even if you go back to your nice simple linear system for determining the net flux from an individual droplet, solving a 100 million by 100 million matrix system is not really plausible. And this matrix is dense, so it's not even like you can get some nice trickery to get around it. So how would you solve this? The natural approach is to look at a periodic lattice problem. This actually fails because of issues at infinity. But it turns out that if you use a continuum formulation, so if you zoom out far enough, the whole thing is roughly going to look like just a droplet, right? This can be formalized, but this is roughly the idea. You create a continuous function which coincides with the net flux at the center of each droplet, and then your linear system actually turns out to look a lot like the Green's function formulation that we solved earlier. And so if you do this, it'll actually give you an explicit solution even for these extremely large arrays. And so finally, without going into all the grisly details, it turns out that you can do this. So what I've plotted here is the prediction for the evaporation rate of the centermost droplet, because that's normally the rate limiting evaporative flux. And so I've plotted the error as a function of basically the number of droplets on one side of your array. The different lines in each color are how far apart the droplets are. The different colors are just slightly different approximations. But what you essentially find is that once you have more than a 100 by 100 array, all the answers are within a sort of 1% error. And interestingly, the upper limit on the validation was actually just the physical size of a matrix fitting in the RAM of the computer that was being used. So that's why we haven't validated any further. And with that, I'd just like to say thank you, and I'd love to take any questions you might have.
Just on your last array, is the idea that you can kind of just solve for a kind of cell problem of, because you had all those fun drop shapes? Is there some way where you can solve in detail a kind of?
Yeah, so this is sort of only solving at the coarse scale.
Right.
If you want to solve at the local scale, you need to do some homogenization theory, and we've had a look at doing that. I don't think it's possible to write down an exact solution, but you can write it down in terms of the doubly periodic Green's function.
But I guess, I mean, if you go back to the really cool multicolored that one,
yes.
Is there some way that you can solve just a cell problem of that and helpfully multiply it all up?
Yes, that's essentially the plan. That's actually something we haven't tried. In this particular case, we were just doing arrays of circular droplets, just to give ourselves, just as a proof of concept.
Right, okay.
But the technique does transfer over. Yeah. I think you could do it. Yeah, you need to do some sort of local calculation and then expand
You don't
it
have
out
a feeling about how amazingly neat that is or not?
Yeah, I couldn't say off the top of my head, but I do think it would work out.
Yeah, that would be cool.
Any other questions?
You mentioned that there were issues in the corners because of the Fourier modes converging. So do you have to use a Fourier decomposition?
For this technique, essentially you don't have any way around it because the technique that we use to invert the L operator relies on decomposing into Fourier modes. In principle, you can write down the integral in such a way that you don't decompose into Fourier modes, but that integral isn't exactly computable. You have to pick it apart to do each term individually.
But is it really exactly computable when you do the Fourier modes? I mean,
no, sorry, yeah, that's fair. Each term is, in the Fourier series is computable. But yeah, that's, it's a shame, but I don't know any way around it, unfortunately.
Right, okay. And just to clarify, which Green's function were you using?
So it's basically the half-space greens functions that you get, yeah.
So I mean, I wonder, is there a smarter choice of greens function, perhaps, that could allow you to do better?
I mean, not that I'm aware of, but what sort of thing are you thinking? Sort of
Well, I'm thinking of taking, if you've got the circular drops, whether there are any that would take that into account explicitly and mash them together, perhaps.
Sorry, yeah, that's actually a really interesting idea. We haven't actually gone down that route. But it's an interesting one because yeah, if you could pick out something that already took into account the circularity, that'd be great. Yeah, no, it's a good idea. I'll have a look at that. Thank you.
Any other questions or comments? Well, in essence, Alex,